Okay, so we may as well get started with the third talk that we've got in this track. So I want to introduce Konrad Hołowiński. I think I've got that right. Talking about cloud-ready, self-healing, scalable IAM architecture and microservices, yes? Konrad, it's yours.
Thank you. So hello everyone. First of all, thank you for coming. So I'm going to be talking a bit about microservices and some challenges that you might have with implementing a microservices-based architecture in your IAM platform if you're building one, or in your company in general. Those are fairly generic for any microservices-based system, but those also are techniques that we are using at Cloudentity to build our IAM platform based on microservices. So starting with that, let's go forward. So the first thing that so microservices have like a lot of buzz around the world, etc. And people are telling microservices this and that, etc., etc. And it's not always well understood what microservices come with and what challenges they bring to the table. So there are several important things that you need to handle when implementing a microservices-based system. So there are some advantages to the architecture, to the architecture style that are obvious for some of you, but maybe not for everyone. So those are, you have like a modular structure. You can build services that are responsible for only particular business features, business requirements. You can split the development into teams responsible for specific specific domains in the organization. One thing that it also brings with it is that you have a really small code base in a particular microservice, and that's really good for that's allowing the company to be really agile when it comes to the fixes, improvements, extensions to a particular service. Like you don't have to extend your big monolithic application, but you can like improve one thing and then redeploy a particular service and improve the so bring the system to the newest version by just upgrading one little part, and that brings that's making the deployment and that independent deployment part of or that advantage turns out to be a really significant advantage over like a regular model. So the other thing is that you can scale what you need, and there were like many talks about containers, Dockerization, all those things that most of you guys probably know, and with those tools in hand, we can like really nicely scale exactly how we want it and not like waste CPU or waste AWS instances or whatever you're using in your application. So that's one of the important things. But there are also problems or challenges. Let's say challenges. Problem is not a good word. So there are challenges with microservices, and the first one is that you are operating on a distributed system, and that brings few things with it, like operational complexity. So you have to spend a lot more time with your DevOps guys, and they have to know much more than they needed to before. And there is like unless you apply some techniques that allow you to make your deployments really smooth and ideally without even using people's time, then this is a big cost. And the next big thing that comes with microservices, the problem are network failures. So essentially, like if you had two nodes, the probability of one node failing for some reason was much smaller than one node failing from thousands of nodes if you have such an infrastructure in place. And I'm going to be talking about how to deal with those challenges and how to make your system really resilient and how to make your system self-heal And I'm also going to talk a bit about scalability and how to approach that. So you can see this is a sample, like a subset of a microservice environment with some of the usual components that you might see in such a system. So you have those green ones are microservices themselves, and so you can see something like an API gateway, which would be familiar to those guys who are actually building with that kind of style. And you can also see event bus, and you can see there are many arrows between those components, especially between those services. And yeah, so what you normally would have to do if you would set all this up manually, you would have to configure all the connections between the different nodes, etc., and configure how they talk to each other, and configure load balancers for all of those. And this seems really complex for bigger ecosystems and systems with tens or hundreds of or thousands of services running at the same time. So yeah, so we have lots of services deployed, and we have several instances of any of those services deployed as well. And we don't really want to worry about environment setup. We don't want to worry about load balances and stuff like that. So we would basically want it to just work without our effort, or a lot of effort. So first thing we would need to do is it would be really good if those services could find themselves, and we don't have to instruct the whole environment to where everything lies and how it should talk to other services that it depends on, etc., etc. So this is a known concept for years, but it's especially important in the microservices world. So service discovery. So basically the first thing that happens is service registration. So what you would do if you build those services out, you implement something that so they are smart in a way that they can find a service registry that they will notify about being available. So basically you start a service and it says to the service registry, hey, I'm here, people can talk to me. So that's the first step in the process. And then you have the actual discovery. So since those services already registered in the service registry, let's imagine we have an order service and it wants to talk to the user service. And what it's going to do is basically going to ask the service registry to grab the information about, hey, do you maybe know where at least one instance of a user service is? And it's going to get some information back, and it can contact that directly. And since services register, but they also deregister, and I'm going to be talking about health checks in a moment, we can figure out that there is a problem with a service. We will always get with a low latency, we will get an information about actual services that can be used and don't have problems with them. Yeah, so the previous slide showed a client-side service discovery, but in some environments when you cannot really use a client-side service discovery because your clients are not smart enough, you would do a server-side discovery, which essentially you have existing applications that you want to integrate with a microservices environment, and what you would like to do is to enable informing the load balancer about the state of the services. So basically, if the services are alive, which ones are healthy, etc., using the same registration mechanism that we have for client-side discovery. So this is the client-side discovery would be preferable, but in case you cannot really use that, that's one other option. And a side note is there are some tools provide a DNS-based client-side discovery. If you're interested in this a bit more, I can talk about that much more later after the presentation. So yeah, the next thing I wanted to talk about is failures. So first thing we have to realize is that network is not reliable. People might tell you that the network is reliable, but that won't be true. And what we would like to do is we would like to detect failures quickly and let the system react. And we would like to let the application or the system heal itself. So basically, whenever a failure is detected, the system takes steps to work around that failure. And for example, if one node died for some reason, we will bring up a new node. And first of all, we will stop sending traffic towards the node that just died. And basically, what we would like to do is embrace failure. Like we would like to actually be prepared for all the failure that might happen in an environment, and we would like to know that our system can react properly to failure. So there are some tools that help us achieve that, and I'm going to mention one. Maybe some of you guys are already using it. This is a tool by Netflix called Chaos Monkey, and this is a part of Simian Army. And Chaos Monkey is a tool that simulates failure. Like if you're working in the cloud, for example, you have like an AWS big VPC and you have lots of services there, etc. Chaos Monkey, you can turn that on, and it's basically going to be causing havoc among your infrastructure. It's going to be like killing nodes randomly. It's going to be blocking network traffic. It can like detach your volume, so simulating like a disk failure. It can like fill your disk up. It can burn your CPU on a machine, like simulate 100% usage of CPU. It can burn I/O. It can simulate network latency, network loss, and stuff like that. And what we would encourage you to do is to run this stuff even in production. That's what Netflix does, for example, and that's what we are doing. Like and even if you are not brave enough to run it in production, you should definitely run it in like testing environments, because you will see problems that you didn't even think will occur, and those can happen. Those are things that can actually happen in the real world. So yeah, that's one interesting tool that I think everyone should use if they like building a distributed system. So I said, so we have tools that can simulate some failure, but we would also like to really quickly know that there is some kind of a problem with a service, so we can replace it or forward the traffic somewhere else. And so we would like to have smart health checks. We would like to have more than just is alive health check, which normally you would just provide like a health check for your application, which would say, okay, this application is running, that's it. So it's good. You can send traffic towards it. And we would like to, instead of that, provide additional health checks based on I/O usage. In most cases, you know how much I/O you can handle. We would like to add health checks based on CPU usage, based on transactions, and even based on some kind of application-specific logic. And the reason we want to do that is that we would like to react faster on failure, because we can know upfront, before our actual system dies and goes totally offline, we can know that there are issues, and maybe we should spin up like 2 more nodes to be able to handle the current load. And this is really important. So that's like a second technique to go into that self-healing kind of world. Now there is one more thing, or maybe 2 more things that I want to talk about. So first are circuit breakers. So I've said that before, remote calls can fail. And since that's the reality, this might lead to some really bad scenarios in your environment, in your microservices-based system. So first of all, imagine you have like several clients calling an unresponsive supplier. For some reason, this node has, or this service has some problems with, handling the amount of data that you are giving it. And if you still will just hit that service with requests all the time from all the sides, and basically that can cause that basically can bring this critical service to a halt. And what that can do in the next step, it basically can cause the calling systems to fail as well, because they will be waiting, for example, they will be waiting till the timeout, until they hit the timeout from the service that is not healthy, and they can get into this state that they are processing more and more requests all the time. And this, in the worst case scenario, could cause like your whole application, all your microservices going down and basically just bringing your system to like a complete catastrophe. And there is a simple pattern and something that you know from like electronics called a circuit breaker, which basically works like this. So whenever you are calling a particular service, if it's responding okay, then you basically your circuit breaker is in a closed state, and you just proceed as normal. Everything works great. But then when you get an error in the response, or for example you get a timeout, you might want to like retry a few times. Maybe this was like a glitch, but after you retry and you actually see that the service that you want to call cannot cope with the answers, then at that point you just open the circuit breaker, and what that means is whenever another request comes into your service, you will not be hitting the service underneath. And the reason is we don't want to kill it. We want to give it a bit of time to actually heal or react on the load, etc., etc. So basically we stop at this point, and we send either an error message back, if that's the case, or we might, in some cases, it's okay to return like a stub response from that particular service. This is okay in cases when the service you are calling is not critical and provides some like side information that's not necessary to have returned. So, and basically when that happens, you have, when requests come and the circuit breaker is open, you just return an error. But every now and then, we'll try to close the circuit. So we'll try to hit the service every like few seconds, or depending on what we configure, and we'll check if the service is now healthy. And if it's healthy, we'll basically close the circuit once again. And we are back to normal. So that's more or less how that stuff works. And I think it's really important, because if you don't implement those kind of protection mechanisms, you might run into serious problems. Okay, a few words about scaling. So the things that I've mentioned here are really important if you want to have like a nicely, quickly scaling solution. So you would like smart health checks, first of all. So you know that there is a problem and you need more nodes, for example. And you know that quicker than when the node goes down, because that's not ideal. You want circuit breakers to prevent failure, across your environment. And you, of course, want service discovery, but because basically, ideally, what you would just like is just to spin a service up, and that's it. And you don't really want to deal with configuration. You want this to happen automatically, etc. And basically, we need to, and we want to scale up and down without operations interaction. So it just does it itself. And of course, on top of that, you can apply existing auto-scaling mechanisms. So you can, based on your rules and the health checks responses, etc., you can scale, and you can use your resources efficiently, which is also, I think, really, really important. All right, since I was talking about the actual IAM, things I've mentioned are pretty generic when it comes to microservices in general, but since we are in IAM industry and we are building a system that we want to integrate as a part of our customers' existing cloud infrastructure. So we have I have two recommendations on the way you can integrate. You either do like a deep integration with your customer, but that means your system has to support, like if you have a really mature model at your customers and they already have microservices in place and they have most of the stuff built really well, then what you would like to do is to be basically invisible, you want to align with what they currently have. And that means that your system, your IAM system, should support the existing service discovery tools And there are many I've mentioned too here. On top of that, your system should support existing configuration servers. So you are not enforcing your own stack on the customer, but can integrate with what they have. And you have to do JWT support for inter-services communication as well. So that's one way to integrate. Now with legacy systems, let's call them that way, with older systems, this is not always the case, and people might complain about the additional complexity of the system. So basically, what we would normally do in that kind of situation, we would expose like an internal API gateway towards our services, and we would basically hide the complexity behind it. And we provide, in that case, we provide the tools for scaling, etc., and management, and make sure that the stuff just works. So those are like some final suggestions. If you are building such a system and would like to integrate, then that's the way we do it. I had 20, right? Okay, so I almost hit it perfectly. So okay, so that's it. Questions?
How you secure microservices? How you make it work, between two or more microservices?
How do you make two microservices?
How you secure?
Oh yeah. So there are like several approaches to this, and so basically we are using. You would use auth-based flows and JWT tokens for the communication, and So depending on the you can either have a simplified model in which you would trust services in a specific like a specific subset of services, and then you can make a simplified model to not go through expensive authorization checks. But in a general scenario, you would just send signed JWTs and verify if they are coming from an appropriate service. Yeah.
So I like the concepts. One of the things that we have been struggling with, I'll try to keep it short. There are 4 aspects of any self-healing architecture. One is orchestration, which second is basically telemetry to read why the failure happened. The third part of it is basically service discovery that you talked about. And the fourth is the circuit breakers and dealing with the failure when service A is not failure by itself, that service B, which is dependent on, is failing, and it should not self-heal. It should rather wait for it to heal and healing by itself. So I haven't found a way to orchestrate, counsel by this, and one of the things on top of it is we want our developers to be transparent of this infrastructure failure management. I haven't found a way to basically integrate circuit breakers with service discovery, with some kind of automation, with telemetry. Basically, it's too cumbersome to implement, and it requires significant amount of engineering effort to meet. So is your learning different from our learning, and how are you actually orchestrating the solution altogether?
All right. So so there are several libraries and tools that you could use for service discovery and also for circuit breakers, but they are kind of distinct. I kind of agree with that. So there is Netflix has this project called Ribbon, which helps a bit if you want to use that. That's a pretty decent implementation. We actually have like an implementation that of our own that connects all those concepts together, and normally circuit breakers would act with one server, but what we wanted to add the discovery of a potentially new healthy service in the middle of the process. So we kind of implemented like our own library that we are using everywhere. So I'm not sure if that's answering your question.
Yeah, I think we are going the same route now.
My question is more about the service discovery part. In a distributed microservices architecture, since we want these services to be loosely coupled, we don't want tight coupling between services. Where does the service discovery come into picture if they were all talking through an event bus?
Sorry, I didn't get the last part.
Well, if the services were communicating through a distributed event bus, where a service A does not really have to know about service B, where does the service discovery comes into picture here?
Oh, I would say that, so yeah, there are like two communication modes. You can either go through events and be totally asynchronous, etc. But that, in my opinion, doesn't always work. Like for some of the APIs, you need actual direct response for not all of the operations that you might want to execute can be implemented with a asynchronous bus. So basically, and we find like, I would say it's always like a case-by-case thing, but we find in our systems we have like, I don't know, 60 to 40, and 60 is maybe direct integration, 40 is going through event bus, when it actually makes sense and it's asynchronous.
Well, cool. That takes us to about the end of the time. So thank you very much, Konrad, and thank you all for being here.